So our exam, our first exam is on Friday. Same time, and the venue is here. So it will cover from section 1.1, 1.2, 1.3, 1.4, and then part of 1.5 if we finish 1.5. So I already set the exam. So you will get, we will review on Wednesday. So the review is on Moodle. I posted it yesterday, so you can check it, and then we'll look at it on Friday, on Wednesday. Okay, let's continue. So we did a summary of the examples that we did, and from example number 8, what we found is the matrix of this form 1, 3, 0, 0 minus 7, 0 minus 0. Okay, so we have 1, 3, 0, 0, 1, negative 1, and then 0, 0, 0. And then in example number 9, what we got is the matrix of that form 1, negative 3, negative 4, 0, negative 7, negative 7, and then 0, 0, negative 2. So that is what we found. Then we found out that this is not the one. Example number 8, we say this is not a, it is not spanning me, right? And this one is spanning. So this will lead us to theorem 3.3 theorem, which says that if the following statements are equivalent for n M by n matrix A. So the following are equivalent for M by n matrix A. So number 1, the matrix equation AX equals to B is consistent for every B, which is an element of Rm. The matrix equation AX equals to B is consistent for every B element of Rm. Number 2, every B, which is an element of Rm, can be expressible as a linear combination of the columns of A. So B, which is an element of Rm, can be expressible as a linear combination of the columns of A. Number 3, the columns of A span Rm, the columns of A span Rm. And then lastly, number 4, every row of A contains a pivot position. Contains a pivot position. So all these are equivalent. So for it to span Rm, then what you can look at in the last one, if all these are related, until the last one here, you find that takes all the pivot positions, like this example of the 9, then all these are pivot positions, all the columns have the pivot positions. Then it means it is span Rm. For this one, we only have 2 pivot positions here. The last column here doesn't have a pivot. So means that it will not span. Any questions?
So be any number that's there.
What's that?
So the pivot position has to be any number other than 0. Is that right?
Yes, yes.
Okay.
It should be consistent. So it should be. What's that? Number 9. Yes, this one is consistent. Yes, it is consistent. Because you see this, so we had another column here, right?
Oh, so that's not the augmented.
Yes, this one is what I meant. Okay, so it is not. So you remember we had B1, B2, B3, right? And then this one we had B1, B2, B3, right? So the last, we had the last matrix here, which it can be B1, B2, B3. And in that case, it might not be B1, B2, B3. So therefore, it will not be consistent. So we should have the pivot position in each of them. So this one, for example, number 8 here is not consistent. Because each of those columns here in the matrix, actually we are looking at the matrix A. We are not looking at the augmented matrix. Okay. Yeah. Okay, now let's now come to section 1.5. Section 1.5. Solution sets of linear system. Solution set of linear systems. So the first one, what we're looking at is homogeneous linear system. Homogeneous linear system. Homogeneous linear system. Okay, now let's look at definition 1.1. Definition 1.1. So what is homogeneous linear system? Okay, so a linear system is called homogeneous linear system if all constant terms in this linear system are 0. If all constant terms in this linear system are 0, i.e., its equivalent matrix equation is of the form AX equals to 0. AX equals to 0. AX equals to 0. So the solution, which is B, the last one, is equals to 0. So every homogeneous linear system is consistent. Every homogeneous linear system is consistent. Every homogeneous linear system is consistent. If AX equals to 0, is the matrix equation equivalent to homogeneous system, then X equals to 0. X equals to 0. So if AX equals to 0 is a matrix equation equivalent to homogeneous linear system, then it means that vector X is also equals to 0. Is also equals to 0. 0 vector. Is a solution of AX equals to 0, which is called the trivial solution, which is called the trivial solution. Solution. Okay, another one. Every non-zero solution of AX equals to 0 is called non-trivial solution. It's called non-trivial solution. If any. So the homogeneous linear system is equivalent to AX equals to 0, and also it is the trivial, it's given as a trivial solution. So what is the criteria for the existence of non-trivial solutions? So 1.2 criterion for the existence of non-trivial solutions. So what is the criteria of getting the non-trivial solutions? Number one, if a homogeneous linear system has no free variables. If it has no free variable, then it only has the trivial solution. So when you reduce the matrix, and then you find out that we don't have the free variables, then it forms the non-trivial solution. It forms the trivial solution. But if you find some free variables, then it means it is non-trivial. It's not trivial. So it means the solution x is not equal to the x, which is a vector x, is not equal to 0 vector. Number 2, if a homogeneous linear system has at least one free variable, then it has non-trivial solutions. Has non-trivial solutions. If we have at least one free variable, then it is non-trivial. It is non-trivial. For example, let's look at example number 1 in this section. For example, so example number 1. Determine whether each of the following homogeneous linear system only has the trivial solution or also has non-trivial solution, and describe its solution sets and describe its solution set. Number A, so example number A, if we have x1 minus 3x2 plus 7x3 equals to 0, minus 2x1 plus x2 minus 4x3 equals to 0, and then x1 plus 2x2 plus 9x3 equals to 0. So this is a linear system, which when we write this in a matrix equation form, then it forms AX equals to 0. Forms AX equals to 0. So we want to see whether we will get the trivial or non-trivial solution following the 2 criteria. So we want to see whether when we reduce this matrix here, we will have the free variables or not. If we will not have the free variables, then it means that it is what? It is giving us the trivial solutions. And also we realize that the homogeneous system should be consistent. So it should be consistent. So let's write the augmented matrix of this. So what is the solution? So first of all, what we need to do is, what you are trying to do is we want to determine whether homogeneous linear system has a free variable or not. We want to see whether it has the free variable or not. So we start by writing the augmented matrix here. So which is 1, -3, 7, and then 0, -2, 1, -4, and then 0, and then 1, 2, 9, and 0. 1, 2, 9. And then we reduce it. Then we reduce to echelon form. So when we reduce this matrix, then 1, -3, 7, and then 0. So we reduce the second and the third row. So to get the new R2, then it is R2 plus 2 R1. And then to get the new R3, then it is R3 minus R1 minus R1. So when we reduce that, then what we get is 0, -5, 10, and then 0. The next one here is 0, 5, 2, and then 0. Then we need to reduce this. So to reduce the last row there, so the new R3 should be R3 plus R2. R3 plus R2. What we get is 1, -3, 7, 0, 0, -5, 10, 0, and then 0, 0, 12, and then 0.
Wouldn't it be -3 in that second row? If it's 2 times R1, it'd be -6.
So 2.
Oh, never mind, I misread the.
Okay. So finally, that is what we get when we reduce. So what can you see from there? So we can see that we have all the pivot positions in each of those columns there, right? So do we have the free variables there? We don't have the free variables. So we don't have. So then it means that, so what we can see from here is that since the given homogeneous linear system has no free variables, it only has the trivial as solution. It only has the trivial solution. So if you don't have the free variables, then it only has the trivial solutions. Okay, example number B. -5. Oh, before we go, so we also said describe the solution set. So it means that the solution set here is X, so solution set. So it means X1 equals to 0, X2 equals to 0, and X3 equals to 0. So X1 equals to 0, X2 equals to 0, X3 equals to 0. So it's giving us the solution, which is the solution set is equals to 0, 0, 0. So it is trivial, it's giving us a trivial solution. Okay, example number B, -5x1 plus 7x2 plus 9x3 equals to 0. x1 minus 2x2 plus 6x3 equals to 0. So we do the same way. We write that in augmented matrix form, and then we reduce it. So the solution. So augmented matrix of this is minus 5, 7, 9, and 0, 1, minus 2, 6, and 0. Then we reduce this. So we reduce that. So what can we do first? So what is the first step here? We can do what? We can switch that. We can switch this, right? We can switch R1 and R2. So R1, we can switch R2. So when we switch, we get 1, -2, 6, 0, -5, 7, 9, and 0 there. And then now, we now reduce this next one here. So R, to get the new R2, then it is R2 plus 5 R1. So we get 1, -2, 6, 0, and then 0, -3, 39, and then 0 there. 0, -3, 39, and 0. So that is what we'll do. So therefore, what can you see from here? We have, yes, we have the pivot position in 2 columns there, right? So therefore, since this is x1, x2, and this is x3, therefore, we can see that x3, the column x3 doesn't have the pivot position, right? So it doesn't have the pivot. So therefore, x3 is what? Is a free variable. Now, so since x3 is a free variable, the given homogeneous linear system has non-trivial solutions. The homogeneous linear system has non-trivial solutions. So it doesn't have trivial solutions. So therefore, we need to reduce this matrix now. So we want to get the solution set. So this is in echelon form. Now we need to reduce that one completely so that we get the solution or the solution set of this matrix. So we already have 1, -2, 6, and then 0, 0, -3, 39, and then 0. So we have the pivot positions here. So we need to reduce this matrix, augmented matrix, completely. So first of all, we need to make this one to be what? 1. So we need to make this to be 1. And then we make this one to be 0. So our new R2 will now be, we multiply by 1/3 R2, which we get 1, -2, 6, and then 0, and then 0, 1, -13, and then 0 there. And then now we make this to be 0. To make this to be 0. So our new R1 will now be R1 plus 2 R2. R1 plus 2 R2. So 1, 0, and then the next one is -20, and then 0, 0, 1, -13, and then we have 0 there. we have 0. So that will be our use. So therefore, here we have the basic variables s, x1 and x2, and three variables, variable s, x3, s, x3. So therefore, the our new linear system here will now be x1 minus 20, x3 equals to 0. And the last one here is x2 minus 13, x3 equals to 0. So that is our new linear system. So what is our solution set? So therefore, our solution set is x equals to x1, x2, x3, which is equals to, so we make x1 here the subject, so that means we take x3 to the other side. So x1, so it will be x3, which is 20, x3. x2 here, we take it to the other side, which is 13, x3. And then our free variable is what? Is x3. Our free variable is x3. Now, in this case, to get a solution set here, then for what? For any x3. Any x3. So you can put any value of x3 here to get a solution. Now, should we put 0? Should we put 0? We say for any x3, right? So the solution can also be 0, 0, 0. The solution can also be 0, 0. Or we can put 1. So 1, 1, 1 there. So the solution x1 will be 20. And 1. No. Now, this now will take us to another section here, which is called the parametric vector form. So the parametric, so 1.3 parametric vector form. Parametric vector form. Now, the solutions of a matrix equations are vectors. The solutions of the matrix equation are vectors, if any. If any. So if we find that it's trivial, then the solutions there are also vectors, which are x1, which is 0, 0, 0. Or we can find a solution which is of this form here, Therefore, what we do is we write out the solution sets. We write out the solution set of the matrix equation equivalent to the linear system. equivalent to the linear system. Like in example 1b. So in example 1b, the solution set here we got as x, which is equals to x1, x2, x3, which we found as 20x3, 13x3, and x3 there. Then in parametric form, then this is equals to, we factor out the value of x there, which is equals to x3, 20 here, 13, and then 1 there, for any x3, for any x3. So that is now in parametric form. So that is the parametric vector form. So in the vector expression, the symbol x3 can be regarded as a parameter. X3 can be regarded as a parameter. So actually, the parametric vector form is found when we don't have the trivial solutions. So when we find that there are some free variables there, so the free variables are now our parameters. So the free variable can be x1, x2, or x3. So those are our parameters. So we write them in parametric form, which is called. For example, example number 2. Example 2. Solve the homogeneous matrix equation AX equals to 0 and writes the solution in parametric vector form, where we have our A equals to 1, 5, 2, -6, 9, and 0, 0, 0, 1, -7, 4, -8, and then 0, 0, 0, 0, 0, and 1, and then 0, 0, 0, and 0. Have our matrix there. So the homogeneous. So this is our matrix. For it to be homogeneous, then x is equals to 0. So when we write the parametric matrix of this, then now put another column there towards zeros. Now let's solve this. So let's get a solution set for this one. So what is the solution set for this? So we write this in augmented matrix form, which will now be 1, 5, 2, -6, 9, 0, 0, and then we put another 0, 0, 0, 1, -7, 4, -8, and then 0. So we don't have this 0 here. And then we have 0, 0, 0, 0, 0, 1, and then 0, and then 0, 0, 0, 0, 0, 0, and 0 there. So if you look at this matrix, so we have our pivot position here. We have our pivot position here, and we also have our pivot position there. So therefore, we will not get the what? Because we have our free variables there. So this is x1, x2, x3, x4, x5, and then x6 there. So, so those are our variables. So we can see that our free variables are at x2, x4, and what? And x5. So those are our free variables. So those are our free variables. Now let's reduce this now completely. So let's now reduce this completely. So we want to make this one to be 0. We also want to make this one to be 0. We want to make this 0 and this one to be 0. So what we get is 1, 5. So we want to reduce. So we can reduce. So we can reduce. Actually, you can reduce R2 to get the new R2 plus 8 R3, and also we can reduce R1. This R1 to be our R1, which is R1 minus 2 R2. R1 minus 2 R2. So once we reduce this matrix now, so first of all, let's start from, let's now start from R2. We want to make this one first of all to be 0. So we want to make this first to be 0. So let's actually start from R2. We want to make this first to be 0. So 1, 5, 2, negative 6, 9, 0, and 0. And then once we make this one to be 0, that means it's R2 minus R2 minus plus 8 R3. So this will be 0, 0, 1, negative 7, 4, and then the last one here will be 0, and then of course this will be 0. And then this is 0, 0, 0, 0, 0, and then 1, and then 0 there. 0, 0, 0, 0, 0, 0, and then 0 there. And then now we come to the, we want to make this now to be 0, this one to be 0. So our R1 will now be R1 minus 2 R2. So what we get is we now get 1, 5, 0, 8, 1, and then 0, 0, then 0, 0, 1, negative 7, 4, and then 0, 0, and then 0, 0, 0, 0, 1, 0, and then 0 here, and then 1 there, and then 0. 0, 0, 0, 0, 0, 0, then 0, then. So that is what we get. So therefore, our basic variable is now x1, x3, and what? And x6, and x6. Our free variable will now be x2, x4, and x5. So that is our free variable. Now, our new linear system in this case will now be x1 plus 5x2. So this is x1, x2, x3, x4, x5, and then x6. And then plus 8, x4, plus x5 equals to 0. Then the next one is x3 minus 7x4 plus 4x5 equals to 0. And then lastly, our x6 equals to 0. Our x6 equals to 0. So then our solution set will now be x1 will now be x1. We take the other ones to the other side. So it will be minus 5x2 minus 8x4 minus x5. Our x2 is free variable. So x2 equals to x2. Our x3 will now be this. We take to the other side, the other ones. So it is x3, which is minus plus 7x4 minus 4x5. And then x4 is our free variable, which is x4. x5 is also our free variable, so equals to x5. And then our x6 is equals to 0, or x6 equals to 0, or x6 equals to 0. That is our solution set. So that is our solution set. So therefore, in terms of now, so our solution set will now be x, which is equals to x1, x2, x3, x4, x5, x6 is now equals to minus 5x2 minus 8x4 minus x5. The next one is x2 here. x3, we said x3 is equals to I'm sorry. So this, there should not be x3 here, right? So because we are taking it the other side. So 7x4 minus 4x5. And then x4 is equals to x4. And then x5 is equals to x5 since they are free variable. And then x6 is equals to 0. So therefore, the parametric equation now will be equals to, we factor out x2, or x2 will be -5. This one is 1, and then the others are zeros. So 1, 2, 3, 4, 5, 6. Plus our x2, our x3 will now be, do we have our x3 here? So our x3, we don't have our x3. Our x4 will now be, we factor out this, so it is -8. The next one here is 0. The next one here is 7. And then the next one here is 1. And then the others are 0, 0. And then our, finally, plus our x5, which will now be -1, 0, -4, 0, 1, and then 0. So that is our parametric equation. Okay. I'll see you on Wednesday, and then we do something small, and then we do the review. Okay. See you on Wednesday. So remember that exam, make sure you read well because for the exam 1, exam 2, and exam 3, I will not allow any material in class. So you just come with your pen. So make sure you revise so well. So just read your notes and you'll be fine.
Last year, the beginning of the class notes, the when you were ready with the definition. Yeah, the last part of this.
It does it.
Yeah, this one.
This one.